Well, hello and welcome to this series of lectures on respiratory physiology. My name's John West, and I'm looking forward to discussing these interesting topics with you over the next few lectures. The material is based on lectures that we've given to the medical students at the University of California, San Diego over the last few years. And it also follows generally my book, Respiratory Physiology, The Essentials, although the lecture format allows us to expand on some material, particularly the topics that give trouble to the students. So where should we start? Well, I happen to believe that the function of the lung is best understood if we first look at its structure. And so this first lecture is going to be on the structure and function of the lung. And what part of the lung should we start with? Well, let's all agree that the primary function of the lung is gas exchange. The lung does other things too. It filters unwanted materials from the blood. It has metabolic functions, and it acts as a reservoir for blood. But by far its most important function is gas exchange, and therefore a good place to start would be at the blood-gas barrier where the diffusive gas exchange occurs. And in this nice drawing here, we can see the lung with the chest wall having been removed. The lung, we can see the right lung here, the left lung here, and between them is the mediastinum, which contains the heart. The air comes into the lung through the trachea, divides into right and left main bronchi, and the airways get smaller and smaller until we eventually get to the alveoli. The blood comes into the lung from the right ventricle through the pulmonary artery. Again, the blood vessels, the small pulmonary arteries, branch many times until we get to the capillaries in the alveolar walls. And it's in the alveolar walls that the blood-gas barrier exists and the gas exchange occurs. The lung is also supported within the chest, and as the diaphragm goes down and the rib cage enlarges, so the volume of the lung is increased, and this is how we take in a breath. Now, if we look in the depths of the lung, we see the alveoli with the capillaries. This is a nice light micrograph taken rapidly freezing the lung, so we believe that it shows the conditions during life. And you can see the alveolar spaces here, and in the alveolar wall, you can see the capillaries. And actually, you can see the individual red cells. And it's the blood-gas barrier which separates the blood here from the gas here, across which gas exchange occurs. Now, this blood-gas barrier is extremely thin, and in fact, we can't identify it in a light micrograph like this. So we need to go to an electron micrograph, and this is shown here. Now, what a beautiful picture this is. You might want to take a print of this and perhaps put it on your refrigerator door or your bedside table. It's just a beautiful electron micrograph, and actually we're going to come back to it from time to time. But let's have a look now and see what it shows us. Here's the capillary in the alveolar wall, which is running across the slide here, and we have alveolar gas on both sides of the capillary here. Within the capillary lumen, we can see the red blood cells and also the plasma. Now, the wall of the capillary is the blood-gas barrier. Blood on one side, gas on the other. And we can see here at the top the very, very thin blood-gas barrier. The thickness of this is only about 1/3 of a micron. Notice we have the scale down here. 1/3 of a micron, which is fantastically thin. Now, wait a moment. What do we mean by 1/3 of a micron? Well, a micron is a millionth of a meter, or a thousandth of a millimeter, and a red blood cell, like we see here, is about 7 microns in diameter. A red blood cell is just clearly visible in the light microscope, and so when we go down to a micron, or even less, as we see here, we're beyond the limits of resolution, and that's why we're using an electron micrograph here. Now let's look at the structure of the blood-gas barrier on this side. And you may notice, by the way, that this side of the barrier is much thinner than this side. In fact, the blood-gas barrier, the capillary, is polarized, so one side has a thinner barrier than the other. Let's look at the thin side first. The outermost layer is the alveolar epithelium, very, very thin cell, as you can see, and here is the nucleus of this, as it's called, type 1 alveolar epithelial cell. Then the innermost layer is the capillary endothelium. We can see it here, and here is the nucleus of the capillary endothelial cell in this beautiful electron micrograph. Between the two layers is the extracellular matrix, or if you like, the interstitium. And on the thin side here, the extracellular matrix is made up of the fusion of the basement membranes of the alveolar epithelium and the capillary endothelium. So the two cellular layers are here, and the fusement of their basement membranes makes up the interstitium. Now, one of the most important constituents of the interstitium is the type 4 collagen in the basement membranes, because we believe that's responsible for the strength of the blood-gas barrier. As you might expect, a barrier that is this thin is rather fragile, and if the pressure inside the capillary rises to abnormally high levels, you can get ultrastructural changes in the blood-gas barrier and leak fluid into the alveolar spaces. That situation is called stress failure. Now let's turn to the lower section here, the lower part of the slide, and you can see that the blood-gas barrier contains additional material. If you look closely, you can see the collagen fibrils in the blood-gas barrier here. Also, if we go over here, and this is a little bit more difficult to identify, but you can see actually a fibroblast, a cell with its prolongations going into the thick side of the blood-gas barrier. Now, this is such a beautiful electron micrograph that I am reluctant to spoil it with graffiti, but that's what we've done. On the next slide, we've just shown the structures, we've labeled the structures, and I've done this so that you can come back sometime if you wish and just refresh your memory on what the various structures are, because it's very important that we understand the structure of the blood-gas barrier. Now, we said that the barrier is extremely thin, 1/3 of a micron in many places. And why is that? Well, that brings us to the principles of diffusion, gas diffusion, through a tissue sheet. And this is shown on this slide. Now, we're going to come back to this slide in much more detail in a later lecture, but we should look just at some of the principles here. What this slide says is that if we have a tissue sheet, for example, something like a postage stamp, for example, then the volume of gas which moves across the tissue sheet here is proportional to the area of the sheet, proportional to a constant, which is called the diffusion constant, and the difference in partial pressure between one side of the sheet and the other. It's also inversely proportional to the thickness of the sheet. And so what this means is that we need as thin a sheet as possible and as large an area as possible. Well, now the blood-gas barrier in the lung, as we've seen, is phenomenally thin in much of its part here. It also has a very large area. In fact, the area of the blood-gas barrier in the human lung is about 50 to 100 square meters, enormous area. You may say, well, how is that prodigious area generated? Well, there are about 500 million alveoli, and in each of the walls of the alveoli, you've got these capillaries with their blood-gas barrier, and that is what allows us to have this barrier that has an enormous area and is extremely thin. Now, I like to think of the lung as a symmetrical organ, with the blood-gas barrier in the middle, air coming in from one side via ventilation, and blood coming into the other side via the pulmonary circulation. And we're going to look at these two systems, the airway system and the blood vessel system in turn, and let's start with the airways. And here we've got a gorgeous photograph of a cast of a human lung. This is made by taking a lung at post-mortem and injecting a polymer into the airways, allowing it to set, and then somebody has taken a fine set of scissors and cut off all the alveoli so that we end up seeing the small airways in the periphery. And as you can see, it's a very, very beautiful picture. The air comes down the trachea here during inspiration, and it meets a junction here, which is called the carina. Carina is Latin for keel. And the airways then divide, the trachea then divides into a right main bronchus, left main bronchus, then lobar bronchi and sublobar bronchi, and so on, all the way down to the alveoli. As we penetrate further and further into the lung, the airways become more numerous, they become narrower, shorter, and they eventually end up in the alveoli. So let's have a look at, first of all, the trachea. Here's the trachea, or the windpipe, it's sometimes called, and it's constructed of cartilaginous rings, as you can see. Here's a section here, and the cartilaginous rings prevent the trachea from collapsing when the pressure outside it is greatly increased, for example, during a cough. However, the posterior part of the trachea, shown here, is membranous in character, and there is some invagination when the pressure outside the trachea is increased. Now let's follow the airways down into the lung, and here's a very nice image. This shows an airway as we enter the lung. This is the airway here with all the cartilage in its wall, and it's accompanied by two blood vessels. One of them is a pulmonary artery, another is a vein. One is blue, the other is red. Which is which? Well, you were right if you said that the blue blood is in the pulmonary artery, because the lung is the only organ in the body where the incoming blood, the pulmonary arterial blood, is deoxygenated, whereas the blood leaving the lung is oxygenated. And that's why the pulmonary venous blood shown here is red, because the hemoglobin is oxygenated, and here in the pulmonary vein, in the pulmonary artery, it's blue. This image, incidentally, was made by freezing a lung so that the events were kept as like they were in life, and then sectioning it and giving us this very nice image here. Now we're further down into the lung. We can see the airway here, and we can see its branches going out. And here's another branch of the airway here. And we're beginning to see the alveoli in what we call the parenchyma of the lung. That's the region, the respiratory region of the lung where the alveoli are, called the parenchyma. Here we are somewhat further down, another beautiful slide. You can see the airway here and its accompanying pulmonary artery here with blue blood. And then over here, you can see a pulmonary vein. Now the artery is still accompanying the airway, but the vein has moved away to the edge of the lobule. And that will continue down to the respiratory portion. And now, of course, we can see the alveoli. They're larger than they were in the previous slide. We're going down further, and the magnification is increasing. Now, this is a more conventional thin section and shows an airway here at the bottom. You can see now that the cartilage has disappeared. There's some smooth muscle in the airway wall here. That's what we can see. And we can very clearly see the alveoli around the airway, and you notice how they're attached to the airway wall. We can also see the accompanying pulmonary artery with its smooth muscle in the wall. We can see the red blood cells, and this hole here is because of some shrinkage during preparation of the section. And you can see from here that you would expect the airway to be pulled open by the alveoli as the lung expanded. As the lung expands, the tension in the wall, in the alveolar walls increases, and this pulls on the airway and expands it, and the same is true of the blood vessels as well. Here we are further down the lung, and this is a very beautiful scanning electron micrograph showing a small airway here and the alveoli attached to the wall on the outside. And again, you can get this impression that the alveoli are going to be pulling the airway open. You'll notice that there are some holes, apparently, in the walls of the alveoli. These are called pores. They're probably closed during life because of fluid lining the alveoli. Now we're even further down the lung, and now we see a few alveoli budding off the airway walls. Now, as we'll see in a moment, there are a number of generations of airways before we see any alveoli at all. But now we get to what we call the respiratory bronchiole, where there are alveoli budding off the airway, and now, of course, these alveoli have a blood-gas barrier, and they contribute to gas exchange. And as we go further down this small airway, we come to airways that have more and more alveoli branching off their walls, as you can see. So there are about 3 orders of respiratory bronchioles. Now we're even further down the lung. Here's an airway here, coming down here. And now we get these blindly ending alveolar sacs, as they're called. And in the ends of the sacs are the alveoli. And then finally, we see the alveoli. We saw this slide before, and we're going to see it again, incidentally. And this is the end of the airway system. And in the walls of the alveoli, we can see the capillaries and the blood-gas barrier here. Now, let's take an imaginary walk down the airways and see what we can find. We'll see some interesting sights. Here's one. Here's a so-called goblet cell. This is in the airway wall, and you can see an opening through which mucus is discharged onto the airway wall. The airway has a mucociliary system, and this is very important in keeping the airway clean. There are cilia, and you can see examples here, and these cilia help to transport the mucus. And here's a good view of the mucociliary system here, and I partly show it to indicate that the goblet cell, which we saw in the last slide, is here in the airway epithelium, but actually more important from the point of view of providing mucus or seromucus material are the glands deep in the airway wall, shown here in a drawing. And you can see a duct takes the mucus up to the airway, and that's where the mucociliary escalator is located. And there are, the mucus is tenacious. If dust particles fall on it, they're swept up towards the epiglottis, where they're tipped over into the gastrointestinal tract. Here are some cilia, beautiful electron micrograph, scanning electron micrograph showing cilia. And also we can see another type of cell called a Clara cell. The function of the Clara cells is not fully understood, but they are believed to secrete another substance which contributes to the mucus lining layer. Here's a drawing which summarizes some of the cells in the epithelium of the airways as we go down from the large airways through the smaller airways, here called bronchioles, down to the alveoli. Initially, you see these tall columnar cells with cilia on top, and maybe the odd, that may be a Clara cell there, or possibly a goblet cell. Then, as we go further down, the height of the epithelial cells decreases, but they are still ciliated, until finally we get to the alveoli, where the cells are very flat, so-called squamous in character. And here's a type 1 epithelial cell here, and here's another type of epithelial cell here. So let's look at the cells in the alveoli. And the first one we should look at is the type 1 alveolar epithelial cell. Now, we saw this before, you remember, in the electron micrograph of the capillary, but here's another nice view. Some people think this cell looks a bit like a fried egg. It has a central nucleus here, like the yolk of the egg, but then spreading away from it are these very long protoplasmic extensions. The cell body spreads a long, long way away from the nucleus. As a matter of fact, when the electron microscope was first introduced and people got their first views of these cells, some anatomists thought that the type 1 alveolar epithelial cell didn't have a nucleus at all. They just couldn't find one. They're few and far between. But of course, they do all have a nucleus, but the protoplasmic extensions are very extensive. That's the type 1 cell. Now let's look at this one, which is, I should add actually, that the type 1 alveolar epithelial cell is the main cell for the structure of the alveoli. It provides the pavement, if you like, of the alveolar surface. Most of the alveolar surface is covered by the type 1 alveolar epithelial cell. It's a fairly lazy cell, doesn't undergo much in the way of metabolism, but it's very important from the structural point of view. Now let's compare that with another kind of alveolar epithelial cell. This is the type 2 alveolar epithelial cell. It's quite different, as you can see. First of all, its shape is quite different. It's got a sort of globular shape here. It's got a ring of microvilli, little sort of hair-like structures around it, like around the edge, a bit like the tonsure of a medieval monk. And you can see the holes through which it's secreting material onto the alveolar surface. Now this material is surfactant, or it's precursor of surfactant. And we're going to be hearing much more about surfactant later on. But just briefly, surfactant is a critically important material because it reduces the surface tension of the alveolar lining layer and therefore confers stability on these alveoli, which otherwise would be very unstable. So the type 2 alveolar epithelial cell is a highly metabolic cell. It's producing this surfactant, and it's quite different, as we can see, from the type 1 cells. Incidentally, we can see type 1 cells around them here. Another cell that we'll see in the alveolus is the alveolar macrophage. Here's another very beautiful scanning electron micrograph showing the alveolar macrophage here. It's a bit like an amoeba. It moves around the surface of the alveoli by amoeboid activity. It can phagocytose particles. It can engulf foreign particles. And its job is to keep the alveolar surface clean. The alveoli do not have the mucociliary escalator. That's limited to the airways. So another kind of mechanism is required to keep the alveoli clean, and this is the alveolar macrophage. This is a beautiful slide because we can see alongside it a type 2 alveolar epithelial cell with its holes and its microvilli, and then in the background here we have the type 1 alveolar epithelial cells, so that's a very lovely slide. This slide shows another alveolar macrophage, and initially you may find it a little bit difficult to work out what's happening. Let me show you. Here's the macrophage here with its nucleus here. And here's the wall of the alveolus running up here and running along here. And so what we've got is a macrophage lurking in the corner of an alveolus. And you'll notice that it contains some material. In fact, these are remnants of surfactant. Surfactant, as we'll hear later on, turns over quite rapidly within the lung, and it leaves remnants shown here, and these are picked up, swept up by the macrophages, engulfed. You can always recognize surfactant material because of its onion skin-like appearance. It's got a lot of layers, and that's what the macrophage is doing here. Now, let's go back a moment and look at our cast of the airways of the lung. As we said before, very beautiful, very elegant system, but what a complicated system. Suppose we wanted to try and work out the mode of gas flow in the lung, in some of the airways of the lung. How could we possibly cope with such a complicated structure as the one shown here? And a very important advance was made by a man called Dr. Weibel a few years ago. He's a Swiss anatomist, a friend of mine, And one day he sat down and he counted all the airways of the human lung. Not only did he count them, but he measured their caliber, their diameter, their lengths, branching angles, and so on. You know, the Swiss are very good at counting things, and he had the patience to do this, and he ended up with a system, a model of the lung, which admittedly is something of an oversimplification, but nevertheless is extremely valuable in understanding the airway system. And this is shown here. He said that if we consider the trachea as generation number 1, this thing Z means generation here, then it divides into 2 daughter airways, the right and left main bronchi. And all the airways divide, as we say, dichotomously. You've got a parent airway, divides into 2 daughter airways. And that continues down through generations 2, 3, 4, and so on, to smaller and smaller airways. And on the average, he said, there's about 16 generations of branching before we see any alveoli at all. So this region of the lung is what is called the conducting zone. It doesn't take part in gas exchange. There are no alveoli, no blood-gas barrier. So this is simply the conducting zone, and it's often called the anatomic dead space, dead because there's no gas exchange within it. The volume of the anatomic dead space is about 150 ml. And then the last of these conducting airways is called the terminal bronchiole. Bronchiole meaning a small bronchus. Terminal bronchiole. And that subtends, or supplies, if you like, a unit of gas exchange, which is called an acinus. That's the unit of gas exchange. And you begin to see alveoli budding off the walls, and therefore these are called respiratory bronchioles. And on the average, there are about 3 generations of these. Then you come to airways where the whole of the wall is lined by alveoli. And these are called alveolar ducts, as you can see, probably about 3 generations of those. And finally, we get to the alveolar sacs, which are blindly ending, and these are covered with alveoli, and of course, that's where the blood-gas barrier is. Now, I said that the volume of the conducting airways, the anatomic dead space, is about 150 ml. The volume of the respiratory zone, which is where the alveoli are, is about 3 liters in the human lung. So the conducting volume is, of course, much less, but it's very important that we understand the difference between these 2 types, these 2 regions of the lung. And we're going to be talking much more about that in the next lecture when we talk about ventilation. So we've been talking about the airways. Now I want to switch and talk about the blood vessels. And here's a beautiful picture showing a cast of the airways on this side, this is the right lung here, and the cast of the blood vessels on this side here. And the blood vessels in this particular cast, the pulmonary artery is shown in red here. That's what he chose to use for the color of the pulmonary artery, and you can see the pulmonary veins in blue. And you can get a general feeling that the pulmonary blood vessels branch in roughly the same way as the airways do. Airways branch, as we've seen many, many times until you get to the alveoli, and is the same is true of the blood vessels. In fact, as I've said before, the small pulmonary arteries tend to run alongside the airways until we get down to the respiratory zone. Now, the next slide shows a small pulmonary artery on the left here, and alongside it is a systemic artery. That's an artery from the rest of the circulation, say from an arm or a leg or somewhere, and they have about the same caliber. Actually, this one is slightly smaller than this, but you'll notice that the walls are completely different. The small pulmonary artery here has rather thin walls, as you can see. This is cut diagonally here and makes it look a bit thicker, but they've got very thin walls, whereas the systemic artery has a very thick wall. A lot of smooth muscle here, small amount here. Why the difference? Because the pulmonary arterial system, the pulmonary vascular system, is a very low pressure system. The pressures in the pulmonary artery are only about an eighth or so of those in the large systemic arteries. And so there's a very big difference between the two. Now, as we go down, let's follow the arteries down, and here we come to an image that we've seen before, but we'll have another look at it. Now we can see a smaller pulmonary artery. We can see the smooth muscle in the wall here, red blood cells, of course, in the lumen, the alveoli around it here, and that is, has its accompanying bronchus here with smooth muscle in the wall. So the smaller pulmonary arteries have small amounts of smooth muscle, and actually it's rather patchy. We'll talk about that again later on. So there's nothing in the pulmonary arterial system which is like the systemic system, where the small arteries have lots of smooth muscle in the walls and they act as throttles. That's not the case in the pulmonary vascular system. And then we get down to the alveoli that we've seen now a couple of times before, the capillaries in the wall and the blood-gas barrier here. Now, if we look at the capillaries in the alveolar wall, face on as it were, and let's imagine that we're in an alveolus and we're looking at the wall of the alveolus, just as I'm in a room and I'm looking at the wall of the room. That's what we're looking at here. We're looking at the alveolar wall face on, and you can see that the capillaries form a very intricate network of capillary segments. And so some people object to calling these capillaries tubes or pipes. They think they form this very intricate network, and we can see that even better if we go to another type of lung. This is a frog lung, an amphibian. There's quite big differences between the lung of a frog and the lung of a mammal like a human, but nevertheless we got a very good view of the capillary segment here. Here's the artery over here, the vein here, and you can see this very dense arrangement of the capillary network, so much so that some physiologists don't like to talk about flow in individual capillaries. They talk about a sheet flow. And an analogy is an underground parking garage where all the air in the garage would be blood, and you've got posts separating the two sides of the sheet of blood from time to time. So that's one way of looking at this. Now here's a drawing showing, and being a drawing you shouldn't believe everything it says, but I think it makes a nice point, and that is it shows that towards the bottom, towards the alveoli here, you've got blood from the pulmonary artery shown in blue here. Notice that it's accompanying the small airway down here to the respiratory region. The blood probably traverses 2 or 3 or 4 alveoli between the end of the pulmonary artery, where it branches into the capillaries, and where it's picked up and taken away in a pulmonary vein. And again, what the artist has shown is the small pulmonary artery in the center of the acinus here, and the pulmonary vein running back along the outside, as we've seen before. Let's have a look at a small pulmonary vein, and that's shown here. Now, how do I know it's a vein? Well, the best way of knowing it is that it's not accompanied by an airway. It's actually very difficult to distinguish a small pulmonary vein from a small pulmonary artery. They both have very thin walls, as this one does. There's a very small amount of smooth muscle in the wall here. I can see a little bit here, very little. And you can see the red blood cells inside the pulmonary vein. And again, you can see how closely the alveoli are applied to the vein. And so it's not a surprise that as you expand the lung and you increase the tension in the alveolar walls, you tend to increase the caliber of the pulmonary veins as you do the arteries. One of the features of this micrograph is that we can see, not easily, but if you look carefully, you can see a potential perivascular space in the outside the vein here. That's important because it's really a potential space, a virtual space, if you like, under normal conditions. But if there is edema of the lung, in other words, if fluid comes out of the capillaries under some conditions, when you raise the capillary pressure, for example, it moves along and collects in these perivascular spaces around the small veins and around the arteries. And you get a cuff of fluid, as we'll see in a later lecture when we talk about pulmonary edema. So that's an important feature of these blood vessels. They have as it were, a sump, a perivascular region here, which can fill with fluid under certain conditions. Now, I've been talking about the pulmonary circulation, but I should emphasize that there is a second circulation of the lung. It's called the bronchial circulation, and it's very much smaller than the pulmonary circulation. Of course, the pulmonary circulation takes the whole of the cardiac output. The whole of the output of the right heart goes through the lung, just as the whole of the output of the left ventricle, the left heart, goes through the rest of the body. And these two circulations are in series. And again, we'll be talking about that in more detail in a later lecture. So the blood flow through the lung is very large. It's something like 5 liters a minute, an enormous amount of blood flow, which is necessary in order to oxygenate the blood. But there's also another circulation shown here. Here's a bronchial artery, not easy to see, bronchial artery coming off the aorta. Sometimes they come off the intercostal arteries. And these bronchial arteries supply the larger airways, the airways down to the respiratory portion of the lung. Of course, the respiratory zone doesn't need any bronchial circulation. It's got plenty of blood from the pulmonary circulation. But the larger airways do not see the pulmonary circulation, and therefore they need a small amount of blood from the bronchial arteries to nourish them. And we should bear in mind that there is a second circulation because it becomes important under some conditions. So let's summarize some of the most important points we've made. We started off by emphasizing that the primary function of the lung is gas exchange. And so that led us to look at the blood-gas barrier in the wall of the capillary deep in the lung. We had a very beautiful electron micrograph showing that. And we saw that the thickness of the blood-gas barrier is fantastically thin, of the order of 0.2, 0.3 of a micron. We also saw that the capillary is what's sometimes called polarized, in the sense that it's very thin on one side, but it's thicker on the other. And the other side is where the fluid exchange occurs. We pointed out that the thin side of the blood-gas barrier is vulnerable because it is so thin, and it's the type 4 collagen in the basement membranes that apparently is responsible for the strength. We then looked at a very beautiful cast of the airways of the lung and saw this series of branching tubes, and we wondered how anybody could make sense of such a complicated structure, but it was very fortunate that the Swiss anatomist Weibel sat down one day, counted all the airways and measured their lengths and their branching angles and their sizes, and gave us a model of the lung which is very useful. One of the features of this model is that the anatomic dead space, the conducting airways, have a volume of about 150 mils. We then took an imaginary walk down the airways to see what we could see en route, and we found that the airways were lined with cilia and mucus, and we have a mucociliary escalator which removes deposited pollutants from the lung. We also saw some interesting cells, the goblet cells that produce some of the mucus. We couldn't see the seromucous glands, which are hidden in the airway wall, but their duct comes up into the airway. We saw the cilia, of course, and also the Clara cells, which apparently are responsible for secreting other materials onto the surface. Eventually, we got down to the alveoli, where we saw that there were two types of alveolar epithelial cells. The type 1 alveolar epithelial cell, which is a bit like a fried egg with a nucleus in the center and big protoplasmic extensions going out. And that's the main cell, the main pavement cell, the main structural cell of the alveolus. We also saw the type 2 alveolar epithelial cell, quite different. It's a globular cell, has microvilli, and we can see the holes in the cell often through which the material that reduces surface tension, so-called surfactant, is secreted. We also saw in the alveoli the alveolar macrophages, because the alveoli do not have the mucociliary escalator to clean them. Instead, they have these macrophages that roam around the alveoli and engulf foreign particles. We then took an imaginary swim down the blood vessels, and we saw that the pulmonary arterial system is a series of branching tubes, very like the airways. In fact, the arteries accompany the airways down to the gas exchanging area. We saw that the walls of the arteries are much thinner on the pulmonary circulation than the systemic circulation because the pressures are so much less. The capillaries form a very dense network of interconnected segments in the alveolar wall, so this is very efficient for gas exchange. We also noted that the small veins have a perivascular space, or perhaps a potential perivascular space, which we'll be talking about more when we come to edema, and the same thing is true of the arteries as well. And finally, we just mentioned briefly the bronchial circulation. It's a very, very small part. It's only a fraction of the pulmonary circulation, but it's important because it is responsible for the nutrition of the large airways down to the gas exchanging regions. So that's the end of our discussion of structure and function. And next time we'll move on and look at the topic of ventilation.